Good evening, everyone, and welcome. This is Robert Haynes with the National Weather Service in Burlington. I see we have people starting to trickle in. We will get started in just a few minutes. Thanks for coming tonight. All right, hello again, everyone. This is Robert Haynes. I see we have a few more people coming in, but we expect a larger number than this, but I guess that they will start to trickle in as we get going with this presentation, maybe a minute or two late. But we will go ahead and get started and go ahead and start setting up the presentation here. So you should be able to see the screen. We have the presentation up. And of course, you have all kinds of different options on the right. We do have a little section for questions. So if during the presentation you have any questions, feel free to type some of those in. There will be a few periods in the presentation where we have some breaks built in to answer any audience questions that we have in there. So feel free to make use of that. And so with that, we will go ahead and get started on our presentation. Thanks again for coming, everyone, this evening, for taking a little bit of time out of your Sunday evening for the Skywarn spotter training course for the National Weather Service in Burlington. I'm Robert Haynes, and I have Rodney with me this evening, and so we'll be co-presenting this presentation together. And so Rodney here will take the first bit of the presentation to discuss what Skywarn is, its layout, and what we do here at the National Weather Service, and part of what our future kind of mission, or maybe even just some of the future initiatives and things that we're doing, just to give you a little bit of experience with who we are at the National Weather Service in Burlington. So I will pass it off to Rodney here.
Yeah, hi everyone. My name is Rodney Chai. I'm a colleague of Robert, and once again, welcome to the Skywarn presentation, and thank you so much for your time. Okay, so we will go through the layout of the presentation, and so of course, we'll talk about how Skywarn operates and why we need the Skywarn program, and we'll give you an overview of the National Weather Service office here in Burlington, Vermont. And we will go through the storm ingredients, the different types of storm, and the National Weather Service warning system. And we would go through, always safety first, and how you can report severe weather to us. And also we'll talk about the increasing emphasis of social science and communication in National Weather Service. So what is Skywarn? Skywarn is a nearly 60-year-old program that trains people to recognize and report severe or hazardous weather to help forecasters make life-saving decisions. So if you one way to see it is you know, kind of like the boots on the ground and the eyes on the ground, so you can help us see what maybe the radar isn't able to see all the time, and it can help us to make you know, timely warning decisions to save lives and property. So why do we need spotters? The United States is the most severe weather-prone country in the world, believe it or not. And a typical year brings, you can, you know, see on the slides here, some of the eye-popping statistics with 10,000 thunderstorms, 1,200 tornadoes, 6 hurricanes, 500 fatalities, and thousands of injuries, and $15 billion in losses. And 98% of all presidentially declared disasters are weather related. And we use all kinds of methods to make weather observations. They can range from things like surface observations to upper air observations you might have heard about or seen, you know, the weather balloon launches. And these balloons, they go high up into the sky and they take real-time measurements of the atmosphere as the balloon goes up into the sky. Computer models, satellite imagery, and as well as radar. But they all have limitations. So here's a kind of like a 4-panel radar imagery from our radar, and you can see that you know, we have all the different tilts. So 0.5 degrees is the lowest tilt, 1.3 degrees, it's a higher tilt, and then it goes up to 2.4 degrees. And you can see based on the different tilts of the radar, and radar, very briefly, and we will cover this later in more detail, you know, basically sends out pulses of energy into the atmosphere. And, you know, and when the radar hits things like raindrops or hail, it will bounce back at different frequencies and it will translate into this radar imagery. And you can see based on the different tilts, you know, you're able to detect different things in the atmosphere. So, you know, so draw your attention to the first step, observe. So you can see the radar, let's say, you know, we have a 1.3 degree tilt. And here in Vermont, in North Country, there's a lot of terrain, and you know, this is actually not the best ideal situation for the radar. You know, ideally the radar should be operating in kind of like, you know, like for example, the Great Plains. You know, you have very flat terrain and no mountains, and you can see as far as you can. And but here there's a lot of mountains, and you know, and this obstacles for the radar, and this is what leads to beam blockage. And sometimes you are not able to see, for example, the, you know, the what is happening in the Northeast Kingdom, or like maybe east of the Green Mountain. And this is why we need spotters to report the ground truth to us, so we know what is happening. And you know, and because that we that's why the report is so important, and it is important to have reliable observers and spotters, so we can, you know, issue warnings based on the reports that you give us. So the next question is, who can be a spotter? Basically anyone, really. And you know, the most important thing is to have an interest in weather, and you know, be reliable, a reliable source of information, and be able to report accurately and relay to us the right information in a timely fashion. So these are just some of the examples of spotters. So anyone. So let's take a step back and discuss what is the National Weather Service and our mission and vision. So mission is like, you know, talk about critical stuff, and then vision is something that we aspire to be. So the mission, you can see, basically is to protect life and property. And you know, do note that the enhancement of the national economy, because we are under the Department of Commerce. So that's the economy aspect to the mission statement as well. And as for the vision, basically is to, you know, to be a weather ready nation. So, you know, ultimately is to prepare the society for and respond accordingly to weather, water, and climate-dependent events, especially nowadays with the impacts of climate change. There's the increased frequency of extreme weather, being, for example, stronger hurricanes and more extreme and prolonged heat waves. These are all, tied to climate change. So where do we service? So we basically service all of Vermont, except for Bennington and Windham counties that are serviced by National Weather Service office in Albany, and also the 4 northernmost counties of New York. And here is the hierarchy. So, as I alluded to earlier, we fall under the Department of Commerce. We are a federal agency. And then within the Department of Commerce, we have the National Oceanic and Atmospheric Administration, or NOAA. And sometimes you would hear, see, in press release or like the media, NOAA and National Weather Service is used interchangeably, but really National Weather Service is kind of like a subset of NOAA, although we are the largest kind of like sub-agency within NOAA. And we are a large country, with basically all kinds of climates you can think of in the world. So, but we are really separated into regions. So here for NWS Burlington, we are in the eastern region, and then you have Alaska region, western region, and so on and so forth. And then within the national hierarchy, there's the different centers. So think of these centers as kind of like the subject matter experts of certain things, So for example, tonight, like there's a chance that we can see the Northern Lights, and they are basically issued by the Space Weather Prediction Center. And those people specialize in astronomy and space weather. And then we also have the Storm Prediction Center in Norman, Oklahoma, that basically issues the severe weather outlooks. Obviously they are located in the Tornado Alley. And then you have the Tropical Prediction Center that basically are the experts for forecasting hurricanes, and they're now in Miami, Florida. And so you can see that these are just some of the centers that that we collaborate with, and different offices in the country. Obviously would collaborate with different centers, more often than the others. So let's see. And then we also have the river forecast centers as well. So the idea is that, so I used to work in the Boston office, and we were co-located with the Northeast River Forecast Center. So the idea is that, well, if you can forecast how much rain is going to fall from the sky, you can forecast how much the river is going to rise. And that's the underlying philosophy behind why the National Weather Service employs both meteorologists and hydrologists. So here is kind of a picture that is a little bit dated, that shows how our operations, an afternoon in operations at NWS Burlington. And for those of you who don't know, we are located in the Burlington International Airport on the 2nd floor. So, as I've alluded to earlier, so weather models can help us assess the ingredients for an upcoming storm. And so, basically, weather models, for those of you who are not familiar with weather models, they are basically kind of like, computer algorithms that, think of like back calculus 1 class in high school. So like, if you have like, let's say, two unknowns like X and Y, you will need 2 equations to solve for the 2 unknowns. So the atmosphere is a lot more complex than that. So, maybe you need like tens of thousands of variables to parameterize the atmosphere. So think about temperature, pressure, dew points, wind speed, wind direction. All these are different variables. And you have, let's say you have 10,000 variables, you would need 10,000 equations. But how much time would it take a human being to solve 10,000 equations? It would take, I don't know, maybe a week. But by then, after you solve for the 10,000 equations, it's really, you're too slow. So the computers, the supercomputers, basically can crunch the numbers in a split second. It's just so robust. And this is basically where the models are run behind the scenes by supercomputers that take up a lot of memory and just tremendous computing power. So basically, in a nutshell, the supercomputers, they do a lot of kind of work behind the scenes so that meteorologists can, we can look at the weather data, model data, and make the critical decisions to safeguard life and property. So, we talk about, in meteorology or atmospheric science, we talk a lot about forecast uncertainty and probability. So what does a 40% chance of rain or precipitation mean? So basically, I would say the 40% chance of rain, even if you ask different forecasters in our office, they might give you a slightly different answer just because of how they understand probabilities. So basically, one way to think about it is 40%. So that's 4 out of 10. So let's say if you have 10, computer models, and 4 out of the 10 say it's going to rain. So that's 40% chance for rain. That's one way of interpreting it. So, and you can see that's summarized by the last paragraph here. And the technology is still growing. So, with the advancement of artificial intelligence or AI and machine learning, this would greatly transform and revolutionize weather forecasting. And, we can basically use the model data and look back into the past, or what we call reanalysis, to forecast the chances of severe weather in future cases. So basically, in a certain set of atmospheric conditions, based on the past data, if we were to see a similar atmospheric setup, we can more confidently say, okay, that tomorrow's storm is going to lead to maybe 50 to 60 mile per hour straight line winds and maybe quarter-size hail with maybe a non-zero chance for a brief spin up. So based on the conditions, we can kind of dig into the archives and, using machine learning, we can really be more accurate in our prediction and hopefully provide more lead time to give people the time to find a safe place if necessary. So we have talked about the kind of the basics of kind of the National Weather Service, why we need Skywarn spotters, and kind of alluded to the fundamentals of severe weather. So let's kind of take a 36,000 feet kind of a overview, if you would like, a panoramic view of where the weather enterprise is right now. And when I say weather enterprise, some of you would say maybe include the broadcast media. So, you might have your favorite TV meteorologist or your favorite TV channel that you get your weather information from. You might also get your weather information from the emergency managers of your town. So, or for those of you who have kids, the school superintendents would have to make the decision whether to have a later start to school or have an early release or cancel school altogether based on the latest weather information. And so what I'm saying is that nowadays meteorologists have recognized that as an agency, it's not so much getting the accurate forecast is still important, but you can have the most accurate forecast, but if it is the message is not being communicated to the communities, and particularly the vulnerable and historically underserved communities, then we have a problem. And and now we have to add the complexities of climate change, which makes extreme weather more extreme and more prolonged. And then you have changing demographics as well. You have to think about, like in Vermont, we have a lot of immigration in recent years, and so we have a growing population whose first language is not English language. So how are we going to get communicate, make sure that the important weather safety messages, the potentially life-saving critical weather information is being communicated to all communities, including the vulnerable communities. And that's why with the latest strategic plan, we have made adjustments for climate change and social science, particularly with regards to how do we best communicate information in an equitable way so that we can best meet the mission. So to give you an example of how the climate has changed the weather pattern here in Vermont, so take a look at the nights with overnight lows at or above 70 degrees in the Burlington area. So when we talk about heat waves, people sometimes focus on the maximum temperature in the daytime. So is it 93, 95, or 97? Okay, all these temperatures are hot, but then the critical component that sometimes people might overlook is, are we able to cool off at night? And this is really relevant for people without the means to air conditioning, so that you have to open your windows and hopefully cool your apartment or your house. But if the overnight lows are stay in the 70s, you're not going to have a chance to cool off at night. And you can see based on climate data, that there's an unmistakable increasing trend in the increasing number of warm nights. So, and this is it's going to make things a lot more uncomfortable for everyone, but particularly people who might be economically disadvantaged, and this could really increase the risk for heat illnesses. And here's a look at the days with mean maximum daytime temperature at or above 85 degrees in the Burlington area. And again, you can see that there's an increasing trend in the number of days at or above 85 degrees. And also 9 of the top 11 warmest years in Burlington's climate history have occurred since the year 2000. And in fact, the top 6 warmest years have occurred since 2010. And as I've alluded to earlier, the Vermont is getting more diverse. And take a look at the racial and ethnic makeup of Chittenden County, which Burlington is located in. And you can see just really a lot more Asians, African Americans, and Hispanics have moved into the area in the last decade. And this is data from the Vermont Department of Health, which is a key partner for us. So, we talked about how we are really part of a weather enterprise to ensure that we safeguard life and property, and we cannot do it ourselves. We really need a coalition of people who can work together. So we have the Skywarn spotters, like all of you. we have the school superintendents. We also have the state agencies like Vermont Emergency Management and Vermont Department of Health. So all these agencies work together to serve the greater good for the public. So you can see here some of the heat vulnerability measures that that Vermont Department of Health used to calculate vulnerability. So, for example, Vermont has an aging population. So, percentage of population of 65 years old and older is getting more. People living below the federal poverty line, people whose first language is not English language, and you also have average number of days, 87 degrees or higher. So, and what about the land use and the type of housing? All this plays a role in calculating the vulnerability index. And taking a closer look at around the Burlington area, you can see even over small distances, you can have great differences in the social vulnerability index. So this is a more generic version of the heat vulnerability index. So this takes into account more factors. So for example, like mobile homes. So we like to tell people, in the event of a tornado outbreak, mobile homes are never safe shelters. Mobile homes will not offer you protection from a tornado. And if we have if you live in a mobile home and if there's a chance for tornadoes the next day, then you really need to think in advance to find a safe place for you to go to in the event that a tornado might affect your neighborhood. So summarizing some of the things we have talked about. So we have talked a lot about weather radiation, but then in the era of climate change, and where the incidence, the frequency of extreme weather is on the rise, we also need to talk about climate radiation. So how do we build resilient communities to not just respond to disasters, but also to increase the community preparedness so we can adapt to more extreme weather, be it prolonged heat waves, or just basically any kind of extreme weather in between. And so the premise here is that extreme and excessive heat impacts vulnerable communities disproportionately. And and some of you might remember just a few years ago we had Hurricane Ida. Now obviously it led to devastation in the south, but New York City, which is not too far away, also bore the brunt of Ida. Now, at the time, it's no longer a hurricane, but there was devastating flash flooding in New York City. And basically, over 20 people died from the flash flooding because they were living in illegal underground apartments. And basically, they drowned to death in their own apartments. And obviously, you can discuss the social economic aspect of the people living in those underground apartments. And as meteorologists, we can only forecast the weather. We can warn for it. There was a flash flood emergency, but those people in the underground apartments, they understood neither English nor Spanish, so they were not able to understand the message in order that they need to get out of their underground apartments. So unfortunately, they perished, and it was kind of a learning moment for the weather enterprise. I mean, obviously, Hurricane Ida was a tragedy, but we want to make sure that we take the right lessons from the tragedy. So that's one of the reasons why National Weather Service is increasingly emphasizing the importance of social science how do we really understand our communities? How do we ensure that we are able to communicate the important and potentially life-saving messages? So that's why it is, like I said before, it is increasingly important to develop an effective coalition with our partners to identify at-risk communities, and secondly, to ensure the message is effectively communicated to them. And this is one of the many ways to increase, preparedness and ensuring that the people who are in the most need receive the weather alerts in a timely fashion. So this was actually not, believe it or not, just a few weeks ago. And parts of, if you live in Chittenden County, you had over a foot of heavy wet snow on Pi Day, so March 14. So this is, in this case, it basically, in a nutshell, we kind of under forecasted the snowfall in the Burlington area, and sometimes that happens. Just the models did not do a good job of picking up the snow band that set up over the area, but in this case, you can see that 3 days prior, we actually put out a message on social media with this graphic right here. So this is the percent chance of 6 inches snow or higher. So you can see really it's kind of like a lock for southern Vermont into parts of north central New York. So but you notice that Burlington area, there's a 53% chance of 6 inches of snow or higher. So in this case, the graphic only tells part of the story, but using the probability of exceedance and the 90th percentile, which is the reasonable worst case scenario, our core partners have indicated to us that that's very helpful for their operations, because, think about it, like the AOT, the Vermont Department of Transportation, they need to know what is a reasonable worst case scenario so they can kind of plan. And if the event does not turn out to be as nearly as bad, you can say that they are prepared for the worst, because it's easier to it's a lot better to kind of over prepare than under prepare. So, and here's another graphic that depicts the uncertainty. So in this case, the Burlington area is circled in red. So this is called the box and whisker plot. So basically, the longer the bar you see in the middle, the greater the uncertainty. So just by looking at this graphic alone, you can say that, well, Burlington can receive anywhere from 4 inches to over a foot of snow. So in this case, that's the difference between borderline winter weather advisory criteria versus winter storm warning criteria snowfall. So there's a lot of uncertainty with this system. And, and again, as I've alluded to earlier, some of you might know, the Storm Prediction Center website, that they issued a severe weather outlook for the whole country. And then we have like, agencies like the Weather Prediction Center that issues the excessive rainfall outlook, and they issue, they're kind of experts in winter weather as well. So we collaborate with them a lot during the winter weather season. So you have all these agencies, and we have, basically a lot of products, and sometimes that leads to confusion. Like people tell us what does wind advisory mean, and what does what's the difference between a wind chill watch and a wind chill warning? And so the Weather Service has recognized that some of the products are kind of confusing, and we have considered public feedback, and so we have you know, embarked on a hazard simplification process over the last few years. And in the next few years, you're going to see kind of like a streamlining of the products that we issue, and hopefully this would improve our communication. And this is actually in part based on partners and public feedback. This is yet another way that we try to streamline our products. So you can see this is called the graphical hazardous weather outlook. And you might remember we had a kind of an Arctic cold outbreak in early February. And so this graphic here basically communicates the excessive cold risk for that day and that night. So you can see, and social science research has told us that you know, there's a color, kind of like a universal color scale. So you know, people are familiar with the traffic light system. So green means good to go, red means no go. So in this case, red is significant threat for excessive cold, but then we also have magenta or purple. And so when magenta or purple shows up, that's kind of an extreme risk for whatever weather hazard that we are communicating. So in this case, it is excessive cold, but it can also just be for like wind. It can be for you know, snow or sleet or even ice. And again, this is an experimental tool here. This is called a brief vulnerability overview tool. It's very new. Just the research is really done in the last couple of years, and basically, you know, I'm sure most of you are familiar with, you know, the severe thunderstorm warnings, tornado warnings, flash flood warnings, and basically this billboard tool, it gives the forecaster or the warning operator. So when he or she is going to warn for, let's say, you know, Chittenden County, and you want to issue a tornado warning. So, you know, using our in-house system, we have all this like, you know, using the GIS software, and we can, the forecaster can kind of have an overview of the community that he or she is warning for, and you know within like say 10-20 seconds that which communities are relatively more vulnerable, and they can be vulnerable, let's say, in the event of a tornado, in the event of a flooding situation. So like, for example, flood prone areas, or winter or wildfire. So, you know, in this case, having this knowledge can allow us to tailor the message a little more so that it's more relevant for the community. And as we have mentioned previously, so, you know, the population is getting more diverse, not just in Vermont, but the whole country. So, for example, there's actually a very significant Spanish-speaking population in Eastern Massachusetts. 30% of Boston Metro is Spanish-speaking. And some of the communities just north of Boston are 70 to 80% Spanish-speaking. So having this knowledge, you know, increases the kind of the urgency to actually have warnings sent out in languages other than English. So in this case, we have the Spanish tweets for severe weather warnings. So there's quite a bit of information. So at this time, we'll take a break, and we'll see if any one of you have any questions about Skywarn, about the National Weather Service in general, or just anything else that comes to mind. Feel free to put a question in the Q&A section.
Good evening, Gage. To answer your question about how do I become a storm chaser with someone? As we don't really have any kind of storm chasing program per se. There is a little bit of a distinction between Skywarn spotting and storm chasing. And so with that, usually the groups that are going to tend to go storm chasing are going to usually be college or university students who are interested in meteorology. It may depend as well. There may be some, I have heard of amateur radio groups before that will do storm chasing, and of course, there might be a various number of social media accounts that do kind of storm chasing. So it's not something that we do here at the National Weather Service. We don't have people that go out and actively chase storms. So it's usually more of a local or community kind of driven effort from usually like something for social media or other kinds of purposes. So if you want to become a storm chaser, I'd encourage kind of, if you are a college student or even a high school student, kind of looking into seeing if there's anyone interested. Otherwise, I would look through different social media channels to see if there are any local groups that do that kind of thing. As far as getting a hold of Reed Timmer or doing what he does, I don't have his personal information, so I don't have that information to give to you. But then, Will, I'll answer your question here. Are Skywarn reports intended to be used primarily for immediate action or for feeding models? That's an excellent question. I really like that, because I think towards the end of the presentation, we'll briefly discuss what co-op and CocoRoS is. Skywarn is usually intended for more immediate action. However, we do also receive reports from people who tell us how much rain they got in the last 24 hours. And sometimes we feed that into our storm maps, especially for snowfall. We do a lot of that as well. So we have a lot of spotters who, on a near daily basis or whenever it rains or snows, they tell us how much that they received. As far as what feeds models, that would require something more like co-op and CocoRoS. That kind of information is treated as more official than even what a trained spotter provides. However, it's also a much more, it requires a lot more dedication to do co-op and CocoRoS, those two different observation type programs.
Right, seeing no further questions for now, we'll proceed with the second part of the presentation. But as always, you can always feel free to put questions in the chat box. So, to be a spotter, always remember safety first. So, here are the 4 principles, and you can be abbreviated as ACEs. So, awareness, communication, escape routes, and safety zones. And again, safety always comes first. So let's talk about heat safety. Summer is coming up. So heat index is a measure of temperature and humidity. So, for example, like let's say like in Phoenix, let's say it can be 95 degrees, but the relative humidity is very, very low. So might not be, that's a dry heat versus you have 95 degrees or with 70-degree dew point. It's pretty oppressive. So, and we issue 2 kinds of heat headlines. The lower tier is heat advisory, basically heat index of 95 degrees or higher for at least 2 hours, and excessive heat warnings for heat indices at or above 105 degrees. So, some of the more common ways to beat the heat is to dress appropriately, dress in light colored clothing, drink plenty of water, and, avoid doing outdoor activities or strenuous activities during the hottest time of the day. And as for severe weather, severe right now we are kind of like in the transition season between winter and severe weather season. So, but now it's a great time to learn to kind of brush up your skills and knowledge on severe weather. So, every single year we have over 280 people, die from thunderstorm-related hazards. So, and here are be it from tornado, flooding, or lightning. And we always tell people, turn around, don't drown. But almost every time you see, maybe not here in Vermont, but you can see in other parts of the country, people drive into flood waters, and it happens all the time. And most of the time you'll probably be fine. You can, but sometimes taking a detour, and not trying to save that 5 minutes can actually save your life, because, for example, a foot of fast-moving water can carry away a small sedan, and 18 to 24 inches of water can carry away most SUVs, vans, or trucks. So, and here this graphic basically shows you how, ideally, the preparation for severe weather doesn't start when you get the warning. That's kind of like too late in the game. So ideally, you should be paying attention days in advance for a potential severe weather event. So, it could be through the Storm Prediction Center Severe Weather Outlook, or through our hazardous weather outlook that we issue ourselves. And then we have, hours before a severe thunderstorm event. Again, perhaps there would be a severe thunderstorm watch, or a tornado watch, or a flash flood watch. And then as we get closer to the event and as the event unfolds, we'll be issuing the warnings from our own office. So, and those are the warnings that you can receive. You can see on the slides, and and again, just kind of knowing where to go, where to get the critical information can save lives. And here's a look at the Storm Prediction Center outlook. So, here in Vermont, most of the time, we will get level 1 or 2, and from time to time we do get enhanced risk level 3 or 5, and we almost never get 4 or 5. Doesn't mean they don't happen, but they're more rare in our area. And don't I would say it out there that you can get tornadoes even in marginal risk scenarios, or sometimes even just general thunder, and there can be brief spin-ups. And we had a couple in the last few years, and there was one in Edison County that has no lightning. Some of you might remember that tornado. So, but let's take a look at the outlook. This is the severe weather outbreak in the South in April 2011. You can see basically you had all, basically level 1 to level 5, but especially over Mississippi and Alabama. So you can see all the high risk. And you might ask the question, so how does the Storm Prediction Center decide, is it going to be enhanced risk or is it going to be high risk? And it really boils down to three different types of hazards: the tornado, straight line wind, and hail. So, and I've mentioned before, so they are the kind of like the subject matter experts in severe weather. So, based in Oklahoma. So, and based on the expertise, they would come out with the probability for each severe weather type. So, in this case, you can see that there's a 45% probability of tornado, 45% probability of straight line wind, as well as hail. So the areas that kind of has the overlap of all this highest probability for each weather hazard types would be given the highest severe weather category. And so the other, so I've talked about hazard simplification, but there's still a lot of misconceptions between what's the difference between a watch and a warning. And this applies for winter weather and severe weather. So watch means that conditions are favorable for the development of severe weather in the coming hours. It's time for you to remain alert and kind of like plan make contingency plans if severe weather does develop. A warning means that severe weather is imminent or ongoing, and you need to take immediate action to safeguard your life and property. So, and you can, how do you get the information? You can get it from NOAA Weather Radio. You can get it from your phone. You can get it from TV or the internet. So, and sometimes just kind of like keep an eye on the sky. And here's another infographic. You have a cupcake watch. You have the ingredients to make a cupcake. A cupcake warning means that the cupcake is already baked. So that's the difference. And sometimes you might get a tornado watch, which is relatively more rare than a severe thunderstorm watch. So the main difference is that we issue the tornado watch in coordination with the SPC when we believe that a tornado threat is going to be, is moderate as opposed to low tornado threat. So basically, if the tornadic threat is low, we would go with a severe thunderstorm watch. And here are the warning criteria for the different severe weather-related warnings. So for severe thunderstorm warning, the hail size needs to be quarter size or more, so 1 inch in diameter or larger. Wind 58 miles per hour or greater. And we do recognize that sometimes it's impossible to get a precise measurement of the wind. So a lot of times we would take like 3 damage or down power lines as kind of like a proxy for that 58 mile per hour wind. Tornado of any intensity. And there's no severe criteria for lightning, but your kids would be able to tell you when thunder roars, go indoors. It rhymes, but this is so true because lightning is a leading severe weather killer in the country. And also, and again, when it comes to flooding, turn around, don't drown. So, and this is a relatively recent development in the Weather Service. So, not all severe thunderstorms are created equal. So you kind of have like a base thunderstorm category. So that's kind of like the lowest tier. So we issue that when it, like we are confident of getting 58 mile per hour wind and or quarter size hail. And then the next level is considerable. So you have 70 mile per hour wind or golf ball size hail. And then the highest tier is destructive wind, so 80 mile per hour wind. That's no joke, and you get baseball size hail. And it can happen in Vermont because the largest hail recorded in Vermont is over 3 inches. And so when we are confident of getting destructive thunderstorm, we would put that destructive tag in the severe thunderstorm warning, and that will activate your phone, because that is actually there's a pretty high threat to your life, so people need to know it immediately. So we have talked about the thunderstorm warning. So what are the ingredients for a thunderstorm? So first, you need moisture. Secondly, you need atmospheric instability, and usually that's from the heating, daytime heating of the sun. Number three, it's forcing mechanism. It's less needed in the summer, so forcing mechanism. So for example, a cold front. That's why a lot of times if you observe on radar, if you see like a line of like thunderstorms, that's usually coincides with the position of the cold front, because that's a lifting mechanism. But in the summer, you have strong daytime heating that can usually compensate for the relative lack of forcing mechanism. And these are ingredients for a generic thunderstorm. So a thunderstorm that's like pop up and relatively short in time, short in duration. But for the storm to become severe, they need something extra. The storms need to become more organized. And this is when we have to talk about wind shear. So what is wind shear? So basically, we talk about the wind that you experience at the surface. It might be blowing, let's say, from the west at 5 miles per hour. But the wind is going to blow very differently, at 3,000 feet on the top of Mount Mansfield, at 10,000 feet. So they can be blowing in different directions. They can also be blowing at different speed. So the difference in wind direction and speed with height is called wind shear. So here's a look at a graphic for thunderstorm development. So you can see, with the daytime heating, and then you have the forcing mechanism, that's the cold front. So, in the summer, that's why we tend to get, our severe weather season here in Vermont typically runs from June to August and sometimes September. And that coincides with the warmest time of the year. So at this point, I will take any questions that you might have.
Hey, yes, we have one question. Is geography, like the Green Mountains, considered a significant forcing mechanism in this area? Sometimes it is, it can be a good forcing mechanism. And sometimes it can also be something that hinders thunderstorms. Say we have a west wind running across the area. Usually when thunderstorms roll across the Adirondacks and then they move down of the mountains, usually there's a little bit of downward motion as a result. And so sometimes we'll see thunderstorms temporarily break up. And then things like the Lake Champlain also affects thunderstorms. Usually Lake Champlain has a negative effect for thunderstorms. And so usually things have a hard time crossing the lake. As soon as they finish crossing the lake, they start coming up a little bit from the mountains again. And so we see thunderstorms usually redevelop again as a front makes it east of Lake Champlain. And then it gets sort of disrupted. So mountains do help upward motion in some sense, but they can also be disruptive of those forcing mechanisms. So it's a fairly complex relationship. So we have another question. What's the best way to look at a storm's severity? We'll go a little bit into some of those details here in the next part of the presentation. We have multiple ways. Usually radar is the fastest way to assess a storm's intensity, but we can also even use satellites. Satellites have grown to incorporate all kinds of different ways to demonstrate thunderstorms' strength and can map lightning now. So sometimes we'll look for the intensity of lightning in a thunderstorm. If there are sudden changes, that's often a good indicator for whether or not a storm is intensifying. And then, are there marine forecasts for Lake Champlain? As far as what we forecast on the lake, we forecast the winds, what we expect the winds to be on the broad lake, as well as just any kind of the sensible weather conditions, like whether or not it'll be raining, sunny, partly cloudy, etc. And then the other thing, of course, is the wave heights. Of course, noting that the wave heights would be a kind of worst case scenario for what you might expect at the lake at any given time. So those are the kind of marine forecasts we provide. As far as what happens really below the surface of the waters, we don't really do as much of that. Is Central Illinois part of Tornado Alley? I know recently there have been some research into considering whether or not Tornado Alley, as we kind of define it, is applicable today, given some of the changing climate. But I think I almost want to say Central Illinois is maybe just east of it, but without a map in front of my face, I'm not 100% certain about whether or not it is in Tornado Alley. I can for certain say they are more prone to tornadoes than we are here in the North Country. All right, so let's go on to discussing some of the, we'll do an overview now here of some of the thunderstorm types and hazards, and then answering a little bit more in depth that way to look at a storm's severity on radar. So let's start with our climatology here. So as Rodney was mentioning and wrapping up there at the end of his presentation, when do we have the best ingredients for thunderstorms? It tends to be June, July, and August. Just in the peak of summer, that's when we usually have the most daytime heating that allows for a lot more upward turning of air, which is favorable for thunderstorms. Also, we also have the development of the Bermuda high. This usually allows for a nice tongue of moisture to move out from the Gulf of Mexico up into our area. And then the other thing is, while areas like Florida typically do not receive fronts in the middle of summer because of how far away they are from the poles, but we can still get weak frontal boundaries here in the summertime that can act as that forcing mechanism, that area that helps thunderstorms to focus in a smaller area. So you can see the quick ramp up in the graphic here of how often we see severe weather in the area. There are occasions where, like you see the number for January and February are not quite zero, but then as you head into the spring season, you can see it quickly ramp up for the area. So really the peak of all of our severe weather is the month of July, when for the years from 1955 through 2021, we've received over 1,000 reports over the span of roughly the last 70 years or so. So that gives you an idea of our overall climatology, and then it rapidly descends heading into the fall and the summer, the winter months, once we lose that better heating. In general, most of our severe weather is going to take place between 1 p.m. and 10 p.m. in the North Country. Part of that is going to be from people sleeping during the overnight hours, but generally, most of our thunderstorms are going to happen in the afternoon, courtesy of heating from the sun. Hail has a similar picture where, again, mostly focused in the afternoon hours across the region. And then finally, tornadoes, mostly focused during the afternoon. Again, though, with a little asterisk that people may not be awake to observe tornadoes during the overnight hours. So as you can see here, here is our map of all of our different severe occurrences of hail across the region. So the larger your dot, the larger your area of hail. And so you can also see characteristics of where we receive the most hail reports. And a lot of times it's going to be focused along road networks because of course people are not going to be happy when hail is hitting their car, but it's also going to be located near towns. So you'll notice a relative lack in the Adirondack Mountains in those counties across northern New York, and as well as far Essex County, Vermont, where the population is just generally not as large. With trees, however, it usually expands into a lot more residential areas as well. Of course, road networks are going to see those clusters as well, because if a tree is down on the road, then we're going to absolutely know about it. But trees are not quite as tied down to these areas of greater population. But still, you're going to have a larger cluster in more urbanized areas like Burlington. And then for tornadoes, there's not really as much of a correlation between population and tornado reports. It's going to be mostly terrain influenced. So mountains have a disruptive effect on the circulation of a tornado. So it's going to be relatively uncommon for some of these more mountainous areas. Although I will point out that it's not unheard of. There is this EF2 that's here in Essex County of New York, that's in the middle of the Adirondacks. And then you have a few across Orleans County that have some of that towards the far eastern slopes there of the very northernmost extent of the Greens as well. So it's not unheard of, but terrain is typically going to have a disruptive effect. Rodney mentioned wind shear as one of the ingredients, and part of how wind shear develops in our area is the channeling of winds up the Champlain Valley. So as we have winds channel through the valley, they're gonna be funneled between the Adirondacks and the Green Mountains. So you have this artificial area where you're always going to have these south winds running into the area, and so as a result, you may have that west wind aloft, and so as a result, you have you get this sort of terrain-driven wind shear that makes tornadoes just slightly more favorable in areas like Middlebury and Addison County. Note this doesn't have some of the most recent tornadoes involved for that area, as this goes from 1950 to 2016. But this can give you an idea of generally it's going to be mostly in these lower terrain areas that have less variable, changeable terrain is going to usually be the focus. All right, getting to that question about the best ways to look at storm intensity, that would be through radar. So what radar is, it's displaying the energy that the radar beam is shooting out across the sky, and all kinds of different targets ranging from, of course, water droplets, reflect some of the energy back towards the radar beam. Other things include, of course, buildings, trains, all these different things show up on radar. But this has been finely tuned and calibrated to really hone in on targets related to, of course, thunderstorms. So we look for these areas to return from these raindrops, and of course, the more energy that's scattered back suggests there are more raindrops in that location. So with that, we can tell the locations with the most rain, snow, or hail based on what energy is coming back to the radar. And so that's how it sees thunderstorms, and also that's how it sees its motion. And so a lot of what you can tell about the intensity of a thunderstorm is how it appears on radar. So there are going to be all kinds of different types and structures to thunderstorms that appear on radar that we use to determine its intensity. But just the basic view of what a thunderstorm is, this is the quote single cell unquote thunderstorm that its most basic classic kind of archetypal characteristic. You have at the beginning the cumulus stage where you have warm air starting to lift higher into the atmosphere. And usually at that point where it starts to get above the freezing layer is when you start to get some of the interaction between cloud ice and supercooled water droplets. That's important for the creation of lightning. And eventually at some point at the mature stage of the thunderstorm, it's going to hit the stratosphere at the point where the atmosphere starts to warm. So at some point there's only so high a thunderstorm can go, as well as you have the increasing size of water droplets, at which a certain point the updraft can no longer sustain it. So for multiple factors, you start to have precipitation. And this rain-cooled air can start to remove that inflow of that very warm air into a thunderstorm. And so over time, you eventually get this this period where it's completely dominated by the downdraft as a result of precipitation, and there's no longer any updraft in the thunderstorm. So at this point, the thunderstorm is starting to dissipate, and it's not long for this world when it gets to that point. So for this, most of the time, when we look at these kind of thunderstorms, we're looking for signatures like the overshooting top just above the anvil cloud at the point where it's starting to enter the stratosphere to indicate how strong that updraft might be. So if that does have that overshooting top, that's likely to indicate that that upward air is very strong, which makes it more likely for damaging winds. Here's a thing of lightning, just to show you what that looks like. So very slow motion video. It starts as once you get the charge collection and separation, at some point you have a step leader, and it's starting its traversal to the ground. And once it makes that connection, bam, there's your lightning right there. So I'll give it one more view of the lightning taking place. So it's a fairly complex process. Lightning doesn't always take the most efficient path to the ground, but once it makes that connection, that's when your lightning discharges. So once that air it's heated up by that lightning bolt, and so that rapid expansion of air and then that contraction of air, kind of why we get the name of the thunderclap, is because basically air is clapping, and essentially. And so that's the noise that you hear whenever thunder is made. Again, we've said it multiple times, when thunder roars, go indoors, because lightning can extend very far away from the thunderstorm. This is an extreme case. The world's longest observed continuous lightning strike is 477 miles. More typically, a thunder, you might be more at risk of a strike for 10 miles away. That's about the distance that you can hear thunder, is about those 10 miles. But just know that lightning can strike well away from a thunderstorm. So whenever we say it, we do mean it, because again, it extends quite far away. So coming back to this idea of looking at a storm structure and what it looks like on radar, a storm spotter can use this information to kind of help them understand what to expect. We started at the most basic level of a thunderstorm, the single cell. So it's a little area of precipitation that's kind of off on its own on the radar. That might not be near any other thunderstorm. It's just kind of alone and in its own area. As we go more down the page, where we're getting more and more organized, heading down this way, you start to get to your multi-cell thunderstorms. These are clusters that are at least somewhat organized. There's usually not a whole lot of wind shear in these kind of scenarios that drive these, but sometimes you can get the development of a gust front along these little clusters of thunderstorms, and that can be the initiation point for new thunderstorms to develop. So you see these little features on radar where you have, say, just these very, very light returns on radar that you can observe. Let's pick a different pen color here. So you can kind of see these small little lines, and that's usually from dust and debris being kicked up from that downburst of a thunderstorm. And that's one way that you can kind of track those. Usually, of course, there's also a lot of wind associated with that. So usually your gust fronts, if you see that on radar, is a good indicator that you have at least some stronger winds. And then, of course, the supercell, known for its classic hook appearance on radar. Supercells can stand alone. They can be their own feature on radar. So a single cell thunderstorm may not be very imposing, but even a supercell can be a single cell thunderstorm. This is just to kind of give you an idea of, as you head more to the right of these images, you're looking at more and more organized stuff. Where it's wind shear is playing a larger part of what's happening here at the on the radar. And then, of course, you have squall lines, where clusters of thunderstorms are well organized, usually due to unidirectional shear. Usually, when you see features like this, where you have the line of thunderstorms, and then you have usually this area of more cool air in the backside of the thunderstorm. That can usually be the point where you have your stronger, say, west winds running into the back of this squall line, and usually that's where you expect the strongest winds and the most precipitation, or any other kinds of thunderstorm organization usually happens in those kind of features. And then finally, on the right is a more extreme instance, the derecho. So sometimes the flow of a thunderstorm can almost kind of create its own little vortex, because naturally, since you have this wind coming into the backside of the system, oftentimes on the northern end, where you do not have quite as many thunderstorms, there's a little bit less less wind as you go throughout. So naturally, you tend to get a little bit of a counterclockwise hook over time on the northern end. And so that's when you get features like the bookend vortex that rides on the northern end of these particularly high-end wind events that take place over time. And so these require usually extreme instability to take place and develop. But over time, a lot of the small thunderstorm scale features will impact radar signatures and tell us a lot about what is happening within the thunderstorm by looking at what we see. I'll briefly step here to answer this question. Do tornadoes spawn in cities, and are they more common on low ground or higher ground? And do tornadoes always form with a wall cloud or supercell? So to answer that question, it depends probably on the city structure. Of course, cities can have tornadoes. I am originally from the Atlanta area, and there have been a couple instances where tornadoes where I was within a few miles of tornado happening within the city. And then they answer the question about low ground or high ground. Sometimes the high ground can play a part in that it can be a little bit colder, or it can be where features have more difficulty, whether features have more difficulty coalescing up there if the terrain is variable. It's a lot less to do with exact elevation and more to do so with do you have a slope or a gradient, or do you have hills and things like that that can disrupt circular flow. So again, it's not to say that tornadoes can't happen in the mountains. We pointed to a couple examples, but it's at least a little less likely. All right. So storm structure can and often does change over time. So what might start as a collection of, or at least a small number of single cell thunderstorms, can become a squall line. So this is the May 4th event from 2018. So just 5 years ago, we had this strong high-end severe event, which began as just a few single cells that eventually merged into a squall line as it went through Vermont. So radar is really the most vital thing to seeing and detecting these changes in a thunderstorm structure. based on that, we can kind of infer what the wind characteristics are just by how a storm evolves over time. So keeping an eye on the sky, you can slowly see these changes take place and develop. Now let's talk about some of the radar signatures that often point to the potential for damage. This is a pure divergence signature. As we noted, the radar is sending a beam out and is getting reflected back some of its own energy that it sends out. And so from that, just like if a police officer is using those devices to measure whether or not you're speeding, Doppler radar works basically the same way. So it can tell whether or not air is moving towards or away from the radar and at what speed. So these areas of red note where wind is moving away, and green where the wind is moving toward the radar. So when we see within kind of the same part of a radar beam, so the radar kind of has all these different scans that it's reading as it spins around and around and around. And so when we see features like wind moving toward and away from the radar in that same kind of horizontal stretch, that's probably an indicator of a downburst wind event occurring. So the example I have on the left is an extreme case. So what's happening is you have dry air that's moving into the thunderstorm, and it's kind of mixing with some of that rain-cooled air and is rapidly descending down to the ground. So naturally, that wind can't go into the ground, so you have the wind coming down from the thunderstorm itself. And so eventually, once it reaches the ground, it has nowhere to go but out. And so as a result, you kind of see this pattern where you have the trees kind of fanning out as this downburst wind expands out and away from the epicenter of where that downburst took place. So that's kind of what that looks like visually. It is an extreme case. More often than not, these type of downburst winds are going to just knock over a few trees for the most part. And so here's just a schematic of how that works. So moisture is an important feature for thunderstorms, but dry air is also going to be something that we consider and take into account as to whether or not a thunderstorm might be capable of downburst wind. So it's a little bit of a complex affair between moisture and dry air, but that entrainment of it and the resulting downward motion and how fast that is important to these features. Straight line winds are usually going to be a little bit more notable. Again, we already pointed out the idea of the rear inflow jet and what that looks like, but much more organized. The squall lines meteorology jargon term is the quasi-linear convective system. So with these groups of thunderstorms and their high winds, you can have at least more organized damage. Of course, it's still going to be, as you can kind of see, pointed in one direction, as the wind line, the area of winds is basically the idea of that straight line is just it's pushing those trees and all of that damage in a single direction. And the derecho stands as the extreme case of that. So when winds are sufficiently strong, that criteria is usually about a handful of hurricane force gusts and extends over a very large area, then that event qualifies as a derecho. So the derecho itself is not the wind, but it's the name of the event. It's sometimes kind of hard to explain, but this is the Adirondack derecho of 1995. It started all the way in Ontario, in far southern Ontario province, really almost more over some of the Great Lakes. And as it moved southeast, it caused significant damage down towards Toronto and just south and west of Ottawa, and then moved into the Adirondacks, Mohawk Valley, and into parts of central New York, into the capital area, as well as parts of the New England coast. All this happened, you can see it made this travel all in just a matter of roughly 12 hours. But this did extensive damage, catching many hikers off guard because it came through overnight. So several hikers were stranded as a result of this, and this caused thousands of acres of tree damage. I think some estimates are as high as 2 million trees or something toppled from this particular derecho. So this is the highest extent of what we can experience. Fortunately, these events happen once every 4 years. We are due for one. We haven't had one in quite some time up this way, but hopefully it will not be this summer. But about once every 4 years is the rough return interval for these kind of storms. So we've talked a lot about the wind and how that looks like on radar, and some of the signatures that you can see on the ground yourself. Let's talk a little bit about hail formation. I'm going to start speeding up here because we are running a little bit towards the end of our time. So hail is going to be, we mentioned that importance of reaching above the freezing layer, and that cycling back and forth of these water droplets or hail, this cloud ice becoming hail. It's continually adding new layers as it moves up and below. So if you were to cut it, you'd actually see all of these layers added on. So hail is going to be more likely the longer the thunderstorm lasts, because it has more time to go up and down and collect layers. It looks like this on radar, where it has this weird kind of appendage at the down beam of the actual thunderstorm itself. And it's called a three-body scatter spike, and occurs because hail reflects the radar beam differently from water droplet. So think of how the water is going to send stuff back to the radar. Well, hail sends some of that radar beam back down to the ground, and then some of that comes back up and then gets reflected off the hail again. And so it comes back as this just very weak signature that seems like it's delayed. And so that's how that happens. And then, of course, the supercell, named solely for the reason, not because it's the strongest of strong storms, but it's because of the fact that they display rotation. So that's the defining characteristic of this. Of course, with this, they tend to last long because you have the separation of the updraft and downdraft. So as a result, large hail is most likely with these, and they can last a little bit longer. And with their rotation, about 1 out of 5 will end up producing a tornado. The separation of the updraft and downdraft can be seen on radar, where the inflow of the thunderstorm is dry and precipitation free. And of course, this is where all the precipitation will be falling. The hook is from debris. All of that stuff being lofted by the tornado is highly reflective. And so that's not actually precipitation, but that's things like bugs and tree barks and things like that being lifted by the tornado. All these different things come together to give the classic hook echo appearance. We had a question about the wall cloud here. Most instances, I think it's going to be like maybe 99% of the time, a wall cloud is going to be associated with a tornado. And it's going to be somewhere between the interface of where there is a lack of precipitation, where inflow is coming in, and the downdraft associated with where precipitation is falling is usually going to be where that takes place. Key difference between the shelf cloud and the wall cloud: the shelf cloud is going to cover the whole horizon, whereas a wall cloud is going to be much smaller. It's going to span a smaller area. So maybe have 50% of the kind of viewing base there, whereas the shelf cloud, again, whole horizon. That's the key characteristic. It forms as a result of the downdraft and the warm interflow. It creates a little turbulent eddy. And so as a result, you get this appearance of where you have that interface again between precipitation and no precipitation. Depending on the flow, the shelf cloud can look a little different from just event to event. We're going to skip over tropical cyclones at this time, and we're going to keep kind of going ahead because we're running low on time. So let's talk about tornadoes. Tornadoes are violently rotating columns of air. The key thing is they're in contact with the ground. They're fortunately rare in this area, with a climatology of about 1 in every 2 years. So again, until it reaches the ground, it is a funnel cloud. Once it is in contact with the ground, you will start to see debris, and that's when you can confidently say that it is a tornado. Tornado has a lot of lookalikes. The main thing is to ask if it's attached to the cloud, or are you even mistaking it for a rain shaft? Sometimes, especially the trick of lighting can sometimes make an area of heavy rain almost look like a tornado. And consider whether or not it's moving up into the cloud, as funnel clouds will always be descending. And then if you ever have any questions, send us video. It's really hard to use just a still photograph image. But having a video with the time of occurrence really goes a long way to helping us match that to radar. And this is an instance of some scud clouds we got from a report, I think, in Messina. So fortunately, most tornadoes are weak. 80% are the 80% of all tornadoes are EF0s or EF1s, but they account for less than 5% of deaths, usually with a shorter lifespan, and hurricane or winds up to hurricane speed, sometimes even less. Most are going to be in this realm up here. About 20% of tornadoes will be EF2s and 3s. Less than 30% of tornado deaths will be associated with this, but usually with the more favorable environment, they'll last a little bit longer. At wind speeds of 110 to 167 miles per hour, they can start picking up cars and things like that. And then EF4s and 5s are when you start leveling foundations, where there is not quite so much one can do to protect themselves. And so as a result, despite only making up 1% of the database of tornadoes, EF4s and 5s cause 70% of tornado deaths. And unfortunately, because the conditions are extremely favorable for these things to develop, they also last a long time. Again, we're going to move on, running for the sake of time, but I'll answer a few questions at the end. Flooding is one of our, we have a saying here, and that saying is hydro first. It is often one of the things that can go unnoticed whenever severe weather is going around. But realistically, flooding is one of the greater weather hazards to life and property. So in general, it's going to be whenever water is moving into a system faster than it can leave that system. Whether it's gradual is more of the idea of flooding, or rapid, the idea of flash flooding. And so the key difference between, of course, that is how fast the water rises. A flash flood can transition into an aerial or river flood warning, but a flood is going to be more gradual from various river rises. So I have the White River on the right with snow melt and rain contributing to that. On the left, I have the Ausable, the east branch of the Ausable River at Ausable Forks, and you can see where you have rain and ice, and all of a sudden you have all of this water flowing as an ice jam breaks up, and all of this flow of water is released in this small area. So flash floods like this are going to take place very rapidly, at which point you seek higher ground as fast as possible. Spring snowmelt is going to be the main reason we experience flash flooding, so March is going to be a big month for that. And then as we head into thunderstorm season, we'll see some more of that. And then sometimes you can get a little bit at the tail of the season due to tropical cyclones and their interactions with non-tropical cyclones. So turn around, don't drown when you experience these things. Again, hydro first, because 2/3 of flood-related deaths are from people driving into those floodwaters. So never drive into floodwaters, because you don't know what might be happening beneath the road. And so here you have a washed out culvert. So as water continues to move into the area, it just washes away the road. But from that one, you can't see it until it's too late. We had a brief mention of forecasting the marine stuff and the winds. It's all about mixing potential. There is less friction over water. You have fewer trees, things like that. Tends to be flatter. Ask yourself, of course, whether the water temperature is warmer or colder. And of course, the channeling through the Adirondacks and the Green Mountains is important. We are at probably the best season for boating, while the relative sea surface temperature right now is quite cold, but the air currently is cool to warm at this time of year, making conditions on the lake stable, very weak winds. And as we head into summer, that continues because water heats very slowly. So as we transition into fall, though, water also cools very slowly. And so as a result, it starts to become much windier on the lake as we transition into fall, as we get colder air moving over that very warm lake water.
And to highlight that, this is our frequency of wind gusts greater than 25 knots on the lake. And you can see that peak is between November and January, but then it rapidly falls off. And then right now we're in May and June, so we are approaching July. We are headed towards our climatological least common, but we can still get those winds and say a thunderstorm. Again, for sake of time, we're going to keep heading here. So we're going to summarize our spotter talk here with this. An effective spotter report answers the following questions. Where are you located? Where was the severe weather? What time did it take place? How long did it last? And of course, who are you? We might not know who you are on the phone. It's going to be, we have constantly rotating shifts, so you may have a different person every day. I've listed here all kinds of different reporting methods. If you are interested in becoming a Skywarn spotter, I go over all of these different reporting methods as well in those emails that I send out. So these are all the different ways. Our storm report page is probably our most used option, where we see most of our reports through this. I always encourage imping, a crowdsourced method of reporting on your iPhone or on the Google Play Store. And then, of course, we had the one question to highlight co-op, CocoRoz, and Skywarn. I think, unfortunately, for time's sake, I'm going to move past this, but I do have some of these old presentations on the Burlington, the NWS Burlington Skywarn page. So I have some of those for reference. And again, we're happy to answer any of your questions about participating in the co-op, CocoRoz, or Skywarn network. Just know that kind of the co-op is the most dedicated of those, where sighting is critical and you take daily observations, where as CocoRoz, it's ideal, but not absolutely required, whereas Skywarn is as often as you desire. It's a completely voluntary network. When it comes to reporting hail, measure it fast, because that hail is melting, and measure it from tip to tip, no matter how misshapen it might be. And then, of course, how to get alerts. We talked about having multiple ways to get warnings via NOAA weather radio, the wireless emergency alert system. If you have it on your phone, have it turned on. And then, of course, a trusted media outlet helps as well. If you have a solid weather app, those are always available. Mobile.weather.gov tries to emulate what an app does. But you can also use even a text and email messaging service is available. I think I can't remember off the top of my head, but you can actually, there's a way to subscribe to those emails for your area. And then also having friends and family. Here's a demonstration of what MPing looks like. You can see all of the different reports. This is most useful in the instances where we have freezing rain taking place. So you can see, it helps us see transition regions on the fly. So to now bring this all together, we talked about who we are and what we do at the National Weather Service, how we do all kinds of outreach events through Skywarn. We do all these educational programs and everything like that to help people learn more about the weather and learn more about us. We talked a little bit about social science and messaging, because what can we do if people don't understand the weather forecasts and the warnings we provide? And so there's a lot of focus, and we're always looking for feedback on how we can tell you the forecast better. So even just doing a better forecast, we're also concerned with how to tell you about that better forecast. So social science is really is becoming a much more becoming a stronger focus for our agency. And so how can Skywarn incorporate into that? I think a lot of it will come down to people telling their weather story and telling us about the things that impact them. So with that, the reliable Skywarn spotter provides some of that ground truth information and tells us some of that story to potentially provide that life-saving information. Storms come in all kinds of flavors. Generally, the more organized, the more likely they are to be severe. While we don't have too much severe weather, it's most common in June, July, and August in our area. Always keep in mind your safety. We never want you to put yourself in harm's way to report information to us. And of course, whenever you are providing reports, be as specific as possible. We may not be as familiar with your roads and cities. Earlier, I indicated that I'm from Atlanta. Well, I've been here now several years. I'm still not familiar with every intersection or landmark in the area. So being as specific as possible helps us pinpoint where active weather is occurring on radar and helps us to kind of tie together those radar signatures that we observe with where you are in the area. So at this point, we'll start wrapping up the presentation here. I have my contact information and Rodney's as well. If you are interested in becoming a spotter, email me or give us a call at the office to inform us that you have listened in and completed the course. And then at this point, we give you our unlisted spotter number, which actually is also here on the presentation, but we ask that you provide a name, an address, and a phone number with which you'll commonly report from. And this helps us, again, whenever you're reporting severe weather, say at home, that helps us to quickly find that location. So we have all kinds of avenues with which you can reach us as well. It doesn't have to be over the phone. It can be through whatever means is most convenient and comfortable for you. And so at this point, I'd like to thank everyone for their attendance. We had an impressive number for a Sunday evening, so thanks for taking some time out of your evening to join us here to learn a little bit more about what we do and how to identify thunderstorms on radar and how to identify significant weather. So at this point, we will allow last minute questions here and then close out for the night. Thanks again, everyone. All right, I'm not seeing any additional questions here being noted, so we'll give a final sign off here. So thanks everyone and have a wonderful evening.